These are 4 common categorisation tasks: sorting, where participants can freely decide how to group stimuli; match to sample; classification; and inference. To solve these problems, students must categorise the animals. Novice learners will categorise according to superficial features, while expert learners will be able to categorise in more than one way and according to much more abstract concepts. This study from Mind, Brain and Education establishes a case for further study into category learning from educational neuroscience perspectives. When presented with a problem requiring classification to solve, novice students sort primarily by the entities or features in the problems, while advanced students sort by the underlying principles or causal relations relevant for solving the problems. Focusing on relations instead of features is critical for abstracting the underlying concepts and applying them in new domains. Categorisation is important to study because a key hurdle to accurate problem solving is knowing which procedure or principle to apply when. The shift from focusing on some superficial aspect of a phenomenon, problem, or reaction, typically the intrinsic or perceptual features of the entities involved, toward a greater recognition of something deeper or more abstract that concerns how all the entities interact or relate to one another, is called the relational shift. A relational shift does not mean that somehow perceptual features are ignored, but they are perceived for how they illustrate or implement the more abstract causal relations. The deep relational structure is perceived in the features themselves. Kelman and Massey used relational methods to teach the mappings between functional expressions and graphs, where graphs are presented and learners select among possible equations, and how to read electrocardiograms, wherein different patterns are presented and learners choose among possible irregularities. These tasks, where learners are presented repeated exemplars, make judgments, and receive corrective feedback in a relatively rapid timescale, have the potential to not just measure concept learning in science, but directly aid learning. Kelman and Massey showed that their function-to-graph learning methods greatly improve student performance, even in comparison to typical problem-solving practice. These kinds of tasks are not meant to replace typical lectures, reading textbooks, nor problem-solving practice, but can offer a useful complementary form. The first benefit listed was that neuroimaging can improve the measurement of cognitive processes and representations. This in turn can contribute to theoretical debates of how conceptual change occurs. The second benefit was that neuroimaging can challenge neuroscientific learning theories. It could challenge many learning theories, actually. It would ensure more representative and ultimately more justifiable generalizable theory. The third benefit is that neuroimaging-based studies can generate recommendations for educational practice. Once behavioural methods have been developed, neuroimaging data could give unique insights into how the conceptual representations change due to iterative corrective feedback. This insight could then lead to a better understanding of what sorts of strategies are most effective at developing expert-like representations in learners. Much credit to all of the sources and authors from which I reported on their work. For further information, please feel free to leave a note in the comments. If you found this video helpful or informative, please click the like button. If you want to see more videos on educational neuroscience, please subscribe. Thank you for watching.